Hello everyone, welcome to Electric Motors course. In this lecture, we will discuss about the Hopkinson test that is performed on the DC machines. So this test is also called as regenerative test, or it is also called as back-to-back test. It is also called as regenerative or back-to-back test. Back to back test. So this test is usually carried out on the two similar or identical DC machines or mechanically coupled to each other. So this is the setup of the Hopkinson test. You can observe here the shaft, the motor, one machine is acting as motor, one more machine is acting as generator. So both are the DC machines. So they both are mechanically coupled with the help of the shaft here. Thus, the full load test can be carried out on these two identical machines without wasting their output powers. So here you can observe the output of the motor is connected as input to the motor, and the output of the generator is connected as input to the generator. So here the maximum part of the input to the motor is coming from the generator only. Whatever the supply we are giving here, we are giving, this supply is to meet the losses in the DC machines, to meet only the losses in the DC machine. So these losses may include the rotational losses here, that is friction and windage losses, iron losses. So to meet those, we are giving the supply here. The output of the generator, you can observe the output current coming from the generator here. So let us understand how this test is performed actually. Okay, so let us understand the circuit first, how this circuit is connected. So here you can observe there are two shunt machines. One is DC shunt motor, this is DC shunt motor, this is DC shunt generator. Both are coupled, mechanically coupled on the same shaft. Okay. So here we are giving the supply. To measure the supply current, we have connected ammeter to measure the current. That is that current is termed as I1, and the current to the motor is I1 plus I2. That is, I1 is the supply current, I2 is the generated current. So it will come from this way. I will tell about this switch, which is connected, when to close the switch. Okay, so motor gets the current I1 plus I2. Among this I1 plus I2, some of the current will flow to the field winding, the remaining will flow to the armature winding. So if you apply KCL at this node, we can say that the current flowing through the armature is I1 plus I2 minus I4, right? The current flowing through the armature is I1 plus I2 minus I4. Similarly, the generator generates the power here. The mechanical output of the motor is connected to the input to the generator. So output of motor is equal to input to the generator. So whatever the current generated at the armature is, some current will flow to the field winding, remaining will flow to the input to the motor. So the current generated by the motor is, field current is I3, this current is I2, so I2 plus I3. The armature current of the generator is I2 plus I3. Now let us understand how to perform this test. Okay, initially we will give the supply to the motor, the voltage supply, we will give the supply. What happens when we give the supply to the motor starts running. The motor starts running, and again it is coupled to the generator. When the generator shaft rotates, it produces the electricity. The same electricity again fed back to the motor. Okay, so this switch will be closed when the voltage across the switch, we have connected a voltmeter, you can observe here. The voltage across the switch, when the voltage across the switch becomes zero, then only we need to close this switch. Then the motor will get the supply from the generator. Why do we need to close the switch when voltmeter reads 0 is because we need to match the generator voltage to the supply voltage. We need to match the generator voltage to the supply voltage, that is, so it should have same magnitude and as well as same polarity. So once you close the switch, the operation is like the output of the generator is connected to the input to the motor, and as well as the output of the motor is connected to the input to the generator. So this is the setup, and this is how we conduct the test. And by putting load on the motor, we can increase the excitation current by using this field, or you can increase or decrease by adjusting these field currents. We can put load on the motor, thereby we can put load on the generator also. Thereby we can note down the different for different loads we can note down the different ammeter readings and the different ammeter readings, the current flowing through all the windings. So I1 represents here is the supply current, I4 represents the field current of the motor, I1 plus I2 minus I4 is the armature current of the motor, I2 plus I3 is the armature current of the generator, I3 is the field current of the generator. So these are the different currents in the test. Okay. So what we need to do? We need to, once you give the supply, we need to check whether this voltmeter is 0 or not. Once if it is not 0, by varying this field, we need to make it 0. So once this becomes 0, we need to close this switch. So once we close the switch, the motor will be supplied with the generator output current. This cycle continues, that is, output of motor is connected to the input of the generator, output of generator is connected as input to this. And so if there are no losses for if you say ideal machines, if there are no losses, the output of the generator is sufficient to drive the motor. Similarly, the output of the motor is sufficient to drive the generator for no loss. So in order to meet the losses, since practically there will be always losses, in order to meet the losses, we are using the supply here. So this supply used to meet the losses in the machine. So now let us calculate the total losses and as well as the efficiency of the machines when working as motor and as well as generator. Okay. So as I said earlier, the input to the motor is nothing but the output of the generator. The input to the motor is nothing but the output of the generator, and the small power taken from the supply. This power taken from the supply is to meet the losses. The mechanical output of the motor after supplying losses will in turn drive the generator. So let us consider V is the supply voltage, current I1 is the supply current, I2 is the field current, that is current supplied by the generator I2, I3 is the field current of the generator, I4 is the field current of the motor, RA is the armature resistance of the each machine, that is motor and generator. Efficiency of both motor and generator. So here we can find out the efficiency of combined efficiency, that is both motor and generator. So from the diagram we can see that the input to the motor is voltage into current. The voltage is applied voltage. Okay, voltage is applied voltage. Current to the motor, input current to the motor is I1 plus I2. It is I1 plus I2. That is, the current is I1 plus I2. That is input to the motor. So V into I1 plus I2 is the input to the motor. V into I1 plus I2 is input to the motor. So output to the motor, we know the formula, efficiency is equal to output divided by input. So if you know the input, we can calculate the output. So output is equal to efficiency into input, that is efficiency into input. Efficiency into input is V into I1 plus I2. It is V into I1 plus I2. So this output of the motor will be given as input to the generator. So generator input will be equal to again output of the motor, that is efficiency into V into I1 plus I2. Now the output of the generator. Now we know the input to the generator. The efficiency of the generator is again output by input, output divided by input. So input to the generator is known. Input to the generator is known, that is efficiency into V into I1 plus I2. The output of the generator, again by using this formula, efficiency into input, efficiency input to the generator is this. So if you substitute this here, this will become efficiency square into V into I1 plus I2. So this is the output of the generator. Also we can write the output of the generator as output current into output voltage. The output voltage is same as the supply voltage because we are matching the magnitude and polarity. So V into I2, the current output of the generator is I2. So V into I2. So both are the output of the generator. So if we equate these two, that is efficiency square V into I1 plus I2 is equal to V into I2. So here V gets cancelled from this equation. V gets cancelled. So efficiency square is equal to I2 divided by this I1 plus I2. So this part I1 plus I2 will come to the denominator here, other side. So efficiency will be equal to square root of I2 divided by I1 plus I2. I1 plus I2. So this is the efficiency of the both generator and motor. But for generator and motor we cannot consider the efficiency will be equal. So what we need to do? We need to calculate the efficiency of both the machines separately. Efficiency of the both the machines separately. So let us calculate the efficiency of the both the machines calculately by calculating the losses of the each machine. So this is the efficiency of the both motor and as well as generator. But we cannot divide this into exactly equally to the motor and generator. So what we need to do? We need to calculate the efficiencies separately. So to calculate the efficiency separately, we need to find out the losses, the constant losses, that is the major loss. The losses are, we have copper losses, stray losses, right? Copper losses and stray losses. So here the stray losses are assumed to be equal, whereas we consider the stray losses are constant losses. Either it may be for motor or generator, the stray losses will be constant. So we assume the stray losses for both motor and generator are equal, whereas the armature and field copper losses are separately determined because the armature current in the motor, armature current in the generator, field current in the motor, field current in the generator are different. So let us find out the armature copper loss in generator, armature copper loss in motor, field copper loss in motor, field copper loss in generator. So we already know the current flowing in the armature of the generator. Current in the generator or armature of the generator is I2 plus I3 square into RA. This is I square R loss. In motor it is I1 plus I2 minus I4 square RA. The copper loss in the field winding of the generator. This is generator. Field winding of the generator is V into I3. The current flowing through the field winding of generator is I3. So the power loss is V into I3. In the same in the motor, it is V into I4. But the total losses in the generator and motor are equal to the power supplied by the mains. So as I said earlier, whatever the supply we are giving, this supply is to meet the total losses of the motor and generator set. The total losses. So power drawn from the supply is V into I1, current I1. So this power drawn from the supply is equal to the total losses of the both the machine, total losses. So this total losses includes the stray losses plus copper losses. Copper losses of armature, of generator, of motor, copper loss of field winding of generator and motor. So from this we need total losses is nothing but it is the supply power, that is V into I1. Stray losses we need. Copper losses we can calculate by using these formulas. Okay, so stray losses will be equal to stray loss. This stray loss will be for both the machines because we are calculating the losses for both the machines because the power supply is to the meet the both the machines losses. So stray loss for both the machines is equal to, so this is the power input, that is V into I1 minus this loss. If you take it to other side, it will become minus the armature copper loss of generator, armature copper loss of motor, field copper loss of generator, field copper loss of motor. So this is the formula to find out the stray loss of the both the machines. So let us assume this stray loss will denote it as Ws. Okay. So assuming that these stray losses are equally divided between the two machines, since this is a constant loss, equally let us divide this stray loss equally to the both the machines. Then this stray loss for each machine will be equal to Ws by 2. Now we got to know this stray loss. So from this stray loss we can calculate the efficiency for both motor and generator. So let us calculate the machine is acting as motor. There is a motor. Let us find out the efficiency of motor. So total losses in case of the motor is there are stray loss plus copper losses. Copper loss of generator armature and copper loss of field winding. So here total losses is equal to stray loss plus field copper loss plus armature copper loss. So efficiency formula is, it is output divided by input power. So input to the motor is, we already know this equation, V into I1 plus I2. So now the efficiency of the motor is equal to output by input. As output is mechanical energy, so what we do, we will convert this output to the input minus losses. So whatever the input we are giving to the motor, it will be equal to, there will be output power plus the losses. So output can be written as input minus losses, so divided by input. Input is V into I1 plus I2 minus losses are armature copper loss of the motor, field copper loss of the motor, stray loss divided by input. So this is the efficiency equation for finding the efficiency of motor. Now we have the generator. Let us calculate the efficiency of the generator. The total losses for generator, again the stray loss plus field copper loss plus armature copper loss of the generator. The output of the generator is V into I2, that is voltage into current. The efficiency of the generator is again output by input. Again here the input is a mechanical energy, so let us convert this input as output plus losses, because output is electrical. So output divided by output plus losses. Output is V into I2 divided by output plus the total losses, that is armature copper loss, field copper loss and stray loss. So by using these equations we can calculate the efficiency of the motor and generator separately. So this is how we conduct the Hopkinson test and calculate the losses and efficiency of the two similar DC machines. That is, one is acting as motor and one more is acting as generator. Thank you.